Optimizing silver selenide for high sensitivity near-infrared imaging.
Colloidal quantum dots are solution-processable nanocrystals on the order of 2 to 20 nanometers. At this scale, an effect known as quantum confinement, where electrons are only allowed to occupy certain energy states, dominates the electron energy landscape. This phenomenon allows quantum dots to emit and absorb photons. Through carefully monitored synthesis, quantum dots of controlled sizes can be created, which allows us to tune the quantum dots to emit and absorb certain wavelengths of light. Quantum dots can be used in a variety of applications. For example, their pure tunable light emission is used to create lasers and color-accurate TVs. Quantum dots can also generate current under light, which is used for solar panels and our current focus, photodetectors. Photodetectors are devices that will generate an electrical response due to the presence of light. Quantum dot solutions can be used to make good photodetectors because photons can excite electrons that will move throughout the quantum dot nanocrystals, generating a detectable photocurrent. Using different quantum dots and combinations of other materials can change how a photodetector behaves. For example, there are quantum dot photodetectors for UV light, and these are used to detect and measure air pollution. Our project is centered around near-infrared photodetectors, which are used for a variety of purposes, like thermal imaging, monitoring crops, and studying planets. Two solutions of silver nitrate and water and 4-terpentyltoluene and 1-dodecane-thiol are mixed and stirred overnight, forming a foamy yellowish silver precursor. The excess water is poured off with a separatory funnel into a beaker for disposal, and the precursor is put into a round-bottomed flask. This flask is then fitted with stoppers, attached to the gas line and placed into a heating mantle. Then the flask is flushed with nitrogen and the precursor is heated to 170 degrees Celsius, turning into a clear yellow liquid. Once it reaches this temperature, the selenium precursor is quickly injected into the flask. The new solution's color will change to a deep black and is stirred for an hour to form small particles.
In order to make the quantum dots into a thin film, we use a technique named dip coating, a process by which substrate material is submerged in conformal coating, then taken out and allowed to drip dry. Because commercial dip coaters cost more than $3,000, we decided to fabricate our own dip coater from scratch. Here's a video of the dip coater we built that cost only $350. Besides electronic components, the dip coater was built entirely using laser cut and 3D printed parts. In addition, it has features including switchable accessories, graphic user interface, auto calibration, and high precision stepper motor. When fabricating a quantum dot thin film device, quantum dots are first dispersed in solution. Then by dip coating, we deposited the quantum dots onto a substrate. After the device is dry, we again dip the device into a ligands change solution, replacing the long ligands with short ligands, bringing the particles closer to each other and thus allow electrons to transport across particles, which makes the device conductive. By repeating the process to a certain extent, we optimize the conductivity and the responsivity of the device. With this quantum dot thin film, we made photodiodes. There are in total 5 layers in our photodiodes. From bottom to top, there are indium tin oxide, which serves as bottom contact, titanium oxide, which is the electron transport layer, silver cyanide quantum dots, which is the photoactive layer, molybdenum trioxide, which is the hole transport layer, and silver nanowires, which is the top contact. Here's a video of a working photoconductive silver cyanide device. When light is off, the device has a very high resistance as shown in the machine. When shining light at the device, the resistance lowers by 10 times, indicating that the light has excited additional electrons, which leads to an increase in current.
The future steps for this project include conducting syntheses for quantum dots to react under different wavelengths of light, like the mid-infrared spectrum, optimizing ligand exchange methods for better devices, and creating vertical devices that act as effective diodes.